this lecture we'll answer two questions. The first question we find out the size of this angle x. This is also defined as angle A and Q. In the second question we find out the area of this circle that is described with this trapezoid ABCD. So we start with the first question. In the drawing we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. So it is known. AB is the diameter of this semicircle. In addition, we know that OS equals to SB. Inside this semicircle, we have this square PQSO. Again, our task is to find out the size of angle A and Q is equals to x. We have to find out the value of x, the value of angle x. So first of all, we know that all the angles inside the square are right angles. So those four angles are all right angles in square PQSO. So this is the right angle. This is also right angle. This is a right angle. And this is also a right angle. AB is the diameter of this semicircle. Therefore, AB is a diameter. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is a right angle plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We also know that all the sides of any square are equal to each other. So in square PQSO, side QS equals to side SO. So QS equals to OS, but it is given the question that OS equals to SB. And from this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. In the next step, we will do a construction, that is to say, we will join points B and Q together by a straight line. And we will extend the straight line BQ by a straight line until it touches the circle, until it touches the semicircle. We define the touching point of the extended line segment BQ with this circle. This point is point N. When doing this construction, we can do the right angle QSB. And the right angle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other with their sizes. According to the rule that in front of equal sides in the triangle, there are equal angles. So if we define the size of this angle as Y, then the size of this angle must be also equal to Y because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, therefore it is true in the right triangle QSB. So which angles we have in the right triangle QSB? Y plus Y is 2Y plus this angle, that is right angle. In total, the sum of those three angles must be equal to 180 degrees. repeat again, 2y plus 90 degrees must be equal to 180 degrees. According to the rule that the sum of the angles in the triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation, and you get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2. And finally we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So surely this is angle y is equals to 45 degrees in inside. And this is also angle y is equals to 45 degrees in size. We joined points B and Q together by a straight line, and then we extended the straight line BQ by a straight line. When we extend the straight line by a straight line, the result BN must be also a straight line. So if we focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line BN at point Q? Here, this angle is equal to 45 degrees in its size, plus this angle that is a right angle, plus this missing angle NQP. Total, the sum of those three angles must be equal to 180 degrees according to rule 3. Again, the sum of the angles on the left side of the straight line BN at point Q must be equal to 180 degrees. That is to say 45 degrees plus 90 degrees plus the side of the missing angle NQP. Total must be equal to 180 degrees according to all 3. 45 degrees plus 90 degrees is 125 degrees. So 135 degrees plus the side of the missing angle NQP. In total must be equal to 180 degrees according to rule 3. Here we subtract 135 degrees from this equation, and we get that the missing angle NQP is equal to 180 degrees minus 145 degrees. 180 degrees minus 135 degrees is equal to 45 degrees. So the missing angle NQP equals to 45 degrees in its size. This is the missing angle NQP is equal to 45 degrees in its size. In the next step, we join points M and N together by a straight line. And we'll join points N and A together by a straight line. When doing those constructions, we're going to do triangle A and B. This is triangle A and B. The subtend on called AB, that is the diameter of this semicircle. And according to rule 7, any triangle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So repeat quickly rule 7. According to rule 7, if a triangle subtends on the diameter of the circle or semicircle, then it is equal to 90 degrees in its size. So in the moment we have a circle. This is triangle ACB that subtend on chord AB, that is the diameter of this circle, and therefore according to this rule 7, triangle ACB must be equal to 90 degrees in its size because it subtends on the diameter of the circle. We can actually implement rule 7 in our drawing. Because in our drawing we have triangle A and B that subtend on chord AB, that is the diameter of the semicircle, and therefore according to rule 7, triangle A and B must be equal to 90 degrees in its size. So in the big right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. This is triangle ABN that subtend on chord AN, and it is equal to 45 degrees in its size. Likewise, we have triangle NMA or triangle AMN. Triangle AMN also subtend on the same chord called AN. And because of the fact that those two triangles subtend on the same chord called AN, they must be equal to each other in their sizes according to rule 16. So repeat quickly rule 16. According to rule 16, triangles that subtend on the same chord are equal to each other. So in the drawing we have a circle. This is triangle AOB that subtend on chord AB. Likewise, we have also triangle ACB. This is triangle ACB that subtend on the same chord called AB. And because of the fact that those two triangles subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, triangle AAB, this is triangle AOB, that is equals to triangle ACB, or alpha equals to beta. So if two or more triangles subtend on the same chord, they are equal to each other in their sizes. You can actually implement rule 16 in our drawing. Why? Because in our drawing we have those two triangles subtend on the same chord called AN, and therefore they must be equal to each other in their sizes. But the size of this triangle ABN is equal to 45 degrees, and therefore the size of this triangle AMN that subtend on the same chord called AN must be also equal to 45 degrees in its size. In the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths, according to the rule that in front of equal angles in the triangle there are equal sides. So side AN is equal to side NB, and therefore the right triangle NB, it is also an associated triangle because side AN equals to side NB. So as you know, if you don't know that the right big triangle A and B, it is also an associated triangle. triangle A and B is an isosceles triangle. So here we can implement rule 24 in the isosceles triangle, triangle A and B. So I click quickly on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the isosceles triangle, triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. The base of the isosceles triangle, triangle ABC is BC. And according to this rule 24, the perpendicular AO to the base BC bisect the base BC. So first of all, AO is perpendicular to BC, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Each half must be equal to BC over 2. Because it bisects the base BC, it means each half must be equal to BC over 2. So the first half is BO, that is equal to BC over 2. The second half is also equals to BC over 2. And BO equals to also equals to BC over 2. So we can actually implement rule 24 in our drawing. Because in our drawing we have the isosceles triangle, triangle A and B. AB is the base of the isosceles triangle, triangle A and B. AB is also the diameter of the semicircle. So I have to know AB is simultaneously, at the same time, it is the base of the isosceles right triangle A and B. And it is also the diameter of the semicircle. If the radius of this semicircle equals to r, then the diameter must be equal to 2r. So if we found out that AB also equals to 2r, AB is the diameter of the semicircle, is equals to 2r. And according to rule 24, the perpendicular from point N bisects the base AB. It bisects the base AB, it means that it divides it into two equal parts. Each part must be equal to AB over 2. AB over 2 is 2R over 2. 2R over 2, 2R over 2 is R. 2R over 2 is R. So the first half equals to R, that is the radius of the semicircle. The second half also equals to R, this is the radius of the semicircle. The question is where the perpendicular from point N to the base AB will touch the base AB. Because of the fact that the perpendicular from point N bisects the base AB, it means that it will touch the base AB at its midpoint. What is the midpoint of AB? The midpoint of AB is the midpoint of the diameter AB. And we know that the midpoint of any diameter is at the center of the circle or semicircle. Again, the midpoint AB is the center, is at the center of the semicircle, that is point O. Therefore, the perpendicular from point N to the base AB will touch the base AB at point O, that is the center of the semicircle. So the perpendicular NO bisects the base AB, divides it into two halves. The first half is AO, that is equals to R. The second half is OB, that is also equals to R. And AO is the perpendicular to AB, that is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We have the rule that says that corresponding angles between parallel lines are equal to each other. We know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. And according to the rule that I mentioned, Those are the two corresponding angles, and they are located between the parallels PQ and OS, and therefore they are equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in its size. According to the rule, the corresponding angles between parallels are equal to each other. Those two angles, that is to say angle NNP and angle NPQ, angle NQP, angle NQP and angle NNP, they are both equal to 45 degrees in their sizes, and each of them subtend on the base NP. Therefore, those two angles are cyclic angles. That is to say, we can block those two angles by circle. It can be inscribed by circle. It is exactly like Rule 16 that says that peripheral angles that subtend on the same chord are equal to each other, and therefore it means that we can, those two angles, they are cyclic angles. We can block them by circle. This is angle NNP, is equals to 45 degrees inside, and it's subtend on chord PN. Likewise, this is angle NQP, it is also equals to 90 degrees inside, and it's subtend on the same chord called PN. And according to Rule 16, those two angles subtend on the same chord called PN, therefore they must be equal to each other. And indeed, they are equal to each other because each of them equals to 45 degrees, and therefore they are equal to each other. For that reason, you can actually inscribe those two angles by circle, because they subtend on the same chord called NP, and they are equal to each other. It is exactly like Rule 16. So, in the next step, I'll prove that actually those two angles that subtend on NP, they create quadrilateral NMQP. So actually, I will prove that those two angles are cyclic by proving that quadrilateral NMQP is a cyclic quadrilateral. What does it mean that a quadrilateral is a cyclic quadrilateral? The red quadrilateral ABCD is a cyclic quadrilateral. Why? Because of the fact that all the four vertices A, B, C, and D, they all lie on the circle itself. So any quadrilateral that all of its four vertices lie on the circle, this is a cyclic quadrilateral. This quadrilateral can be inscribed by circle. A quadrilateral can be blocked by circle. You can see that the red quadrilateral ABCD is blocked by the circle because of the fact that all the four vertices A, B, C, and D lie on the circle itself. So any quadrilateral that all of its four vertices lie on the circle, it is a cyclic quadrilateral. So in the next step, I'll prove that quadrilateral NMQP is a cyclic quadrilateral. In order to prove that quadrilateral NMQP is a cyclic quadrilateral, I copied triangle NQP in your page. In triangle NQP, we have this angle NQP. This is equals to 45 degrees in size, and it subtends on the base NP. Okay, this is triangle NQP. In triangle NQP, this angle equals to 45 degrees. Angle NQP equals to 45 degrees in size, and it subtends on the base NP. So triangle NQP is a cyclic triangle because of the fact that all the triangles in the world are cyclic quadrilateral, are cyclic. All the triangles in the world can be blocked by circle, can be inscribed by circle. Therefore, you can definitely inscribe this triangle NQP by this circle. So inscribe this triangle NQP by this circle. Why triangle NQP is inscribed by this circle? Because of the fact that all the three vertices N, P, and Q, they all lie on the circle itself. Therefore, triangle NQP is inscribed by this circle. So this operation can do it definitely because all the triangles in the world are cyclic, and therefore triangle NQP is also a cyclic quadrilateral. Now we focus on this angle NQP that is inscribed by this circle, and it's subset on chord NP. We also another angle NMP that is also subset on the same chord PN, and it is also equals to 45 degrees in size. All the other angles that are not located on the circle itself, like this angle PQN, that point P is located on the circle itself. This is angle PMN, that the vertex M also located on the circle itself. All the other angles, for example angle PLN, that its vertex is not located inside this circle, but it is located outside this circle. Actually all the angles that where vertices are located outside this circle will be less than 45 degrees. Like this angle actually measures this, the size of this angle PLN, the size of this angle PLN is equal to 49 degrees, that is less than 40. It is equal to 49 degrees, that is less than 45 degrees. Actually all the other angles, you can try and draw another angle that is located outside this circle. The vertex is located outside this circle, and it's obtained on chord PN, it will be less than 45 degrees. Likewise, all the angles that obtained on chord PN and are located inside this circle, that associate their vertices are located inside this circle, like this angle PON, that's obtained on chord PN, and its vertex is inside this circle. The size of this angle PON equals to 85 degrees in its size. So all the angles that their vertices are located inside this circle and subtend on chord PN will be greater than 45 degrees. The only angles that subtend on chord PN and are equal to 45 degrees are the angles that their vertices are located on the circle itself. Like this angle PQN, its vertex Q is located on the circle itself, and this is angle PMN, that its vertex M is located on the circle itself. So all the other angles that where their vertices are not located on the circle itself will be either less than 45 degrees or will be greater than 45 degrees. Therefore, I can conclude that only the angles that their vertices lie on the circle itself and the subtend on chord PN will be equal to 45 degrees. The other angles will be either less than 45 degrees or more than 45 degrees, like those two angles. For that reason, we can definitely rotate this angle PQN around this circle without changing its size. The vertex NP doesn't move. In this way, we get all the angles that are equal to 45 degrees in their sizes. They are equal to 45 degrees in their sizes because by rotating the angle, we will not change the size of the angle. We rotate the vertex Q around this circle without changing the size of the circle, without changing the size of the angle. The axis PN is not moving. In this way, we get infinite angles, and all of them are equal to 45 degrees in their sizes. One of those angles and their subset on chord PN. One of those angles will be angle PMN, that is size is 45 degrees. We will not change the size of the angle, so angle PMN will be equal to 45 degrees in its size, and it's subset on chord PN. It is exactly like this angle PMN, that it's subset on PN. You can see here that angle PMN also subset on PN, and it is equal to 45 degrees in its size. In the next step, we join points M and Q together by straight line. By doing all those operations, we actually created a quadrilateral NMQP. This is quadrilateral NMQP that is definitely inscribed by this circle. It a cyclic quadrilateral because of the fact that all of its four vertices, N, M, Q, and P, they are all located on the circle itself. For that reason, the quadrilateral NMQP is a cyclic quadrilateral. So you can write down that quadrilateral NMQP is a cyclic quadrilateral because of the fact that all of its four vertices, N, M, Q, and P, they lie on the circle itself. All lie on this circle itself. Therefore, quadrilateral NMQP is a cyclic quadrilateral. So write it down. We actually found out that we proved that quadrilateral MNQP is a cyclic quadrilateral. We have a rule that relates to a cyclic quadrilateral. According to the rule, the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So first of all, we know that quadrilateral NMQP is a cyclic quadrilateral, therefore I'll block this quadrilateral by a circle. The red circle blocks this quadrilateral NMQP because of the fact that all the four vertices N, M, Q, and P lie on the red circle. Therefore, it is inscribed by this red circle. So according to the rule that I presented to you, this quadrilateral NMQP, that is a cyclic quadrilateral, the sum of those two opposite angles must be equal to 180 degrees. This is angle NPQ, this is angle NMQ. So the sum of those two opposite angles must be equal to 180 degrees according to the rule that I presented to you. So write it down. If you found out that this is angle NPQ in quadrilateral NMPQ plus the opposite angle NMQ. In total, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I presented to you. And again, the cyclic quadrilateral NMQP, the sum of its two opposite angles equals to 180 degrees. Angle NPQ is a right angle. Plus this is angle NMQ. In total, angle NMQ equals to 45 degrees plus x. 45 degrees plus x. And it is equals to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. So 135 degrees plus the missing angle x, that is the angle that we were looking for in this question. In total, they are equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle x equals to 180 degrees minus 135 degrees is 45 degrees. So here, this is the missing angle x, that is also defined as angle AMQ. So angle AMQ is equal to x is equal to 45 degrees in its size. So we finish with the first question. In the next step, I'll present to you the second question and solve the second question of this lecture. our task in the second question is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB. The whole quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. What is the area of trapezoid ABCD? Actually, the two parallel bases DC and AB are defined. The two parallel sides DC and AB are defined as the bases of the trapezoid ABCD. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. Repeat again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So we have in the drawing a circle that is described by trapezoid ABCD. Those two angles are both right angles. We know that side AB of trapezoid ABCD equals to 3 units in its length. The area of this trapezoid ABCD equals to 3 square units in its size. Here. Again, our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, we'll define the relevant point to this question with letters. We'll define the center of this circle. This point is point O. Likewise, we'll define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent DA with this circle. This point is point F. And finally, we define the point of tendency of tangent AB with this circle. This point is point G. We also define the radius of this circle as X. In the next step, we will join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore G is the radius of this circle, is equals to X according to our definition. So here we can implement rule 1, I repeat quickly rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle. This is tangent AB, that is tangent to this circle is point M. In addition, we have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle is also 90 degrees, and this angle also is also 90 degrees according to this rule 1. So we can actually implement rule 1 in our drawing. Well, because in our drawing, we have the radius OG that is equals to x. The radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, that is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and E together by straight line. O is of course the radius of this circle, is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral DEOF we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be this rectangle if not a square. So we relate to quadrilateral DEOF as a rectangle, although it is actually a square. So quadrilateral DEOF is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOF, side EO must be equal to the opposite side DF. But EO equals to x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrilateral FODE, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Quadrilateral FOGA is 4 rectangles, therefore we can relate to quadrilateral FOGA is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its length. So in total, the length of side DA of trapezoid ABCD equals to x plus x, that is 2x. DA equals to 2x units in its length. The next step we define the length of side DC of trapezoid ABCD as A. AB equals to 3 units in its length. According to what is given in the question, and CB is the missing side, so leave it as it is. Here, I've already proved that in the previous lecture that DA plus CB equals to DC plus AB according to rule 2. So I'll not repeat on the same proof again. DA plus CB equals to DC plus AB. So in trapezoid ABCD, we already proved that DA plus the opposite side CB is equal to DC plus the opposite side AB. This is true according to rule 2. Repeat again, in trapezoid ABCD, we have already proved that side DA plus the opposite side CB equals to DC plus AB. This is actually true in any triangle, according to rule 2. It is true in any trapezoid, of course. DA equals to 2x plus CB. CB is the missing side, so leave it as it is. And it is equals to DC. DC equals to A, according to our definition, plus AB. AB equals to 3 units in this length, according to what is given as the question. So in total, we should all know that two x plus CB equals to A plus 3. Here we subtract 2x from this equation, and we get that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB. This equals to A plus 3 minus 2x units in its length. In the next step, we will do a construction. This is to say, from point C, we will draw perpendicular on AB again. From point C, we will draw perpendicular to AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we're going to do the big quadrilateral DCMA. The big quadrilateral DCMA. We have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral DCMA, we have 4 right angles, and therefore, according to rule 5, can relate to quadrilateral DCMA is a right angle because it has 4 right angles. Write it down. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side MA or AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. AM equals to A. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM, but DA equals to 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. So write it down. MB The missing line segment MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is 8. So the total we found out that MB equals to 3 minus AM is in this length. MB equals to 3 minus AM is in this length. In the next step, I'll copy the right big triangle CMB in a new page. This is the right triangle CMB. I'll copy it in a new page. And we'll implement the Pythagoras theorem on this right big triangle, triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle CMB that I covered from the original drawing. In this right triangle CMB, CB squared, that is the square of the hypotenuse, must be equal to CM squared plus MB squared according to the Pythagoras theorem. So write it down. CB squared, that is the square of the hypotenuse, must be equal to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared equals to A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. Plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So total, I have found out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. Here we will open the brackets on both sides of this equation according to the algebraic identity that says that A minus B squared equals to A squared plus B squared minus 2 times A times B. So A plus 3 minus 2x squared equals to, according to the algebraic identity that I mentioned, it will be equal to A plus 3 squared plus 2x squared, 2x squared is 4x squared, minus 2 times A plus 3 times 2x. And it is equal to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A, that is minus 6A. We'll open the brackets of this expression and get that A plus 3 squared equals to A squared, plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, plus 4x squared, and it is equals to minus 2 times 2x is minus 4x, so in total This expression equals to minus 4x times a plus 3. And it is equals to 4x squared plus 9 plus a squared minus 6a. So here we have a squared on both sides of this equation. So a squared will get cancelled. We have also 9 on both sides of this equation, so 9 also get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also get cancelled. So we cancel all those two expressions. In this side of the equation, we left only with 6a minus 4 times x times a plus 3, and on the other side of the equation we left only with minus 6a. In total we should find out that six a minus 4x times a plus 3 equals to minus 6a. Here we will add 6a and also 4x times a plus 3 simultaneously to this equation, and we get that 6a times 6a plus 6a is 12a, and it is equals to 4x times a plus 3. Here we divide this equation by 4, and we get that 12a over 4 is 3a, so 3a equals to 4x over 4 is x, so this expression in total equals to x times a plus 3. So if we found out that 3a equals to x times a plus 3, here we divide this equation by a plus 3, and finally we get that x equals to 3a over a plus 3. And again, if we found out that x equals to 3a over a plus 3 units in its length. X is the radius of the circle. In the next step, we will calculate the area of trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. What is the area of this trapezoid ABCD? The area of trapezoid ABCD is equals to the sum of its two parallel bases, that is to say DC plus AB, DC plus AB, times the height. The height is cm because of the fact that it creates 90 degrees with the two parallel bases, so it is times the height cm over 2. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say DC plus AB times the height cm over 2. DC equals to A plus AB. AB equals to 4 units in its length according to what is given in the equation, times the height cm. Cm equals to 2x over 2. In total, we will know that the area of trapezoid ABCD equals to a plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So we cancel 2, we left only with a plus 3 times x. In total, we should find out that the area of trapezoid ABCD is equal to a plus 3 times x square units in its size. But it is given us the question that the area of trapezoid ABCD is equal to 3 square units. So if we can substitute the area of trapezoid ABCD by 3 square units. We do it now, we get that 3 equals to a plus 3 times x. 3 equals to a plus 3 times x. Here we will divide this equation by a plus 3. And we get that x equals to x equals to 3 or a plus 3. So now we find that x equals to 3 or a plus 3. Again, we found out actually that 3 equals to a plus 3 times x. Okay? 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. We do it now and we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled. And we're left only with 3 equals to 3a. Equals to 3a. Here we divide this equation by 3 and we get that a equals to 3 plus 3, that is 1. So a equals to 1 unit in its length. And we already found out that x equals to 3a over a plus 3. Therefore we can substitute a in this equation by 1 because a equals to 1. We'll do it now and we get that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total we found out that the radius of the circle x is equal to 3 quarters units in its length. Our task is to find out the area of this circle that is described by this trapezoid ABCD. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. But again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3 quarters, therefore x squared is 3 quarters squared. 3 quarters squared is 3 squared, that is 9, over 4 squared, it is 16. So in total, we found out that the area that we are looking for in this question, that is the area of this circle, is equal to either 9 pi over 16 square units in its size, or in terms of numbers, it is equal to 1.767 square units in its size. And that is the answer to the second question. Repeat again, we have found out that the area that we're looking for this question, that is the area of this circle, is equals to either 9 pi over 16 square units in its size. So in terms of numbers, the area of this circle equals to 1.767 square units in its size. So we finish the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the size of angle AMQ is equals to x. We have to find out the value of angle x. So in the drawing, we have a semicircle. Point O is the center of the semicircle. AB is the diameter of the semicircle. We know that OS equals to SB. Inside this semicircle, we have this square PQSO. Again, our task is to find out the size of angle AMQ that is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So those four angles are all right angles in square PQSO. AB is the diameter of this semicircle. AB is the diameter. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. We also know that all the sides of any square are equal to each other. So in square PQSO, side QS equals to side OS. QS equals to OS. But this is given us the question that OS equals to SB. And from this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. Okay? QS equals to SB. In the next step, we did a construction. That is to say, we joined points B and Q together by a straight line, and then we extended the straight line BQ by a straight line until it touches the circle, until it touches the semicircle. We define the touching point of the extended line segment BQ with this semicircle. This point is point N. By doing this construction, we created the right triangle QSB. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. According to the rule that in front of equal sides in the triangle, there are equal angles. So if you define the size of this angle as 1, then the size of this angle must be also equal to 1 because they are equal to each other. So again, in the right triangle QSB, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in the triangle is equal to 180 degrees. So which angles we have in the right triangle QSB? We have y plus y, that is 2y plus 90 degrees. In total must be equal to 180 degrees. So 2y plus 90 degrees in total must be equal to 180 degrees. Here we subtracted 90 degrees from this equation. We found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees, we divided this equation by 2 and we found out that y equals to 90 degrees over 2 is 45 degrees. So this is the missing angle y that equals to 45 degrees in size. This is also the missing angle y that equals to 45 degrees in size. We join point B and Q by a straight line. So BQ is a straight line. Then we extended the straight line BQ by a straight line. When we extend the straight line by straight line, the result BN must be also a straight line. So if we focus on the left side of the straight line BN at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. But again, in the left side of the straight line BN at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have in the left side of the straight line NB at point Q? We have 45 degrees plus 9 degrees. plus the size of this missing angle NQP in total must be equal to 180 degrees according to rule 3. And again, 45 degrees plus 90 degrees plus the missing angle NQP must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees, so 135 degrees plus the size of the missing angle NQP in total they must be equal to 180 degrees according to rule 3. Here we subtract 135 degrees from this equation. If I found out that the missing angle NQP, the size of the missing angle NQP is equal to 180 degrees from 135 degrees, that is 45 degrees. So the size of this angle NQP is equal to 45 degrees. In the next step, we join points M and N together by straight line, and we also join points N and A together by straight line. By doing all those constructions, we get the deal perpendicular A and B. Perpendicular A and B, this is perpendicular A and B. That's obtained on chord AB, that is the diameter of the semicircle, and according to rule 7, any perpendicular that's obtained on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Perpendicular A and B, so obtained on AB, that is the diameter of this semicircle, and therefore according to rule 7, perpendicular A and B must be equal to 90 degrees in its size. So in the right triangle A and B, 45 degrees plus 90 degrees plus the size of this missing angle in total must be equal to 180 degrees. That is the sum of the angles in the triangle. Therefore this third missing angle must be equal to 45 degrees in its size. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. According to the rule that in front of equal angles in the triangle, they are equal size. So in the right triangle A and B, side A equals to side A and B, therefore the right triangle A and B is also an associated triangle. And again, the right triangle A and B is an associated triangle, because side A equals to side A and B. In the right triangle A and B, AB is the base of the right triangle and the associated triangle. And here we can implement rule 24 in our drawing. According to rule 24, the perpendicular to the base of an associated triangle bisect the base. So the perpendicular from point N to the base AB of the associated triangle A and B bisect the base AB. This is to say, divides the base AB into two halves. Each half must be equal to AB over 2. But AB is also the diameter of the semicircle. So if the radius of this semicircle is R, then the diameter must be equal to 2R. Therefore AB also equals to 2R, it is the diameter of the semicircle. So the perpendicular from point N bisect the base AB. Each half must be equal to AB over 2. AB over 2 is 2R over 2, because AB equals to 2R. 2R over 2 is R. So the first half is R, and the second half is also R. But the question is where the perpendicular from point N will touch the base AB. The base AB is also the diameter of this semicircle. The perpendicular to the base bisect the base, therefore the perpendicular to the base must touch the base at its midpoint. Because it bisects it means that it must touch the base at its midpoint. What is the midpoint of the diameter AB? The midpoint of the diameter AB is always at the center of the semicircle, that is point O. Okay, therefore the perpendicular from point N must touch the base AB at point O, that is the center of the semicircle. So the perpendicular NO bisect the base AB, so each half equals to R. It is a perpendicular, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We have the rule that corresponding angles between parallels are equal to each other. In a square PQSO, the opposite sides are equal to each other, are parallel to each other. That is to say, PQ is parallel to OS. In square PQSO, side PQ is parallel to the opposite side OS. So those two angles are defined as corresponding angles, and they are located between the parallels OS and PQ, and therefore they are equal to each other. according to the rule that corresponding angles between parallel lines are equal to each other. But this is the right angle according to our construction. Therefore, this angle must be also equal to 90 degrees in its size because they are equal to each other according to the rule that I mentioned. So, we have here angle AMN, triangle AMN, subtend on called AN. Likewise, we have triangle ABN. This is also subtend on the same chord called AN. And because of the fact that those two triangles subtend on the same chord called AN, they must be equal to each other in their sizes. But the size of this triangle ABN is 45 degrees, and therefore the size of this angle AMN must be also equal to 45 degrees. Okay, so here we have those two angles. They are both equal to 45 degrees in their sizes. They subtend on the same base NP, and therefore quadrilateral NMQP is a cyclic quadrilateral according to rule 16. If we block this quadrilateral by a circle, then we get that it obeys to rule 16 because we have those two triangles that subtend on chord PN and the same chord called PN. And according to rule 16, if two or more triangles subtend on the same chord, they must be equal to each other in their sizes. You see that those two triangles are equal to each other, each of them equals to 45 degrees, and therefore they are equal to each other. So it obeys to rule 16. Therefore, the quadrilateral NMQP is a cyclic quadrilateral. I'll show you proof that this quadrilateral NMQP is a cyclic quadrilateral in detail. So, why quadrilateral NMQP is a cyclic quadrilateral? First of all, what is the definition of a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral that all of its four vertices lie on the circle. This is the red quadrilateral ABCD. All the four vertices of quadrilateral ABCD, A, B, C, and D, they all lie on the circle itself. Therefore, quadrilateral ABCD is inscribed by this circle, or it is blocked by this circle. It is a cyclic quadrilateral. So we have to prove that quadrilateral MNQP is a cyclic quadrilateral. That is to say, all the four vertices NMQP they lie on the circle that blocks it. In order to prove that quadrilateral NMQP is a cyclic quadrilateral, I copied this triangle NQP. This is triangle NQP. In triangle NQP, angle NQP equals to 45 degrees in size and it subtends on the base NP. So I copied triangle NQP in a new page. This is triangle NQP that I copied from the original drawing. Angle NQP in triangle NQP is equal to 45 degrees in its size and it subtends on the base NP. On the base NP. So we know that all the triangles in the world are cyclic quadrilaterals, are cyclic triangles. That is to say, you can block all the triangles in the world by a circle. Therefore, you can block this triangle NQP by a circle. So I block this triangle NQP by this circle. Now we have angle NQP. This is peripheral angle that subtends on chord NP. Again, in the drawing we have angle NQP, peripheral angle NQP. This equals to 45 degrees in size and it subtends on chord NP. Here we have angle NQP. This equals to 45 degrees in its size and it subtends on chord NP. Likewise, we have also angle NMP. This is also equals to 45 degrees in its size and subtends on the same chord called NP. What happens if we draw an angle that subtends on chord NP and it is located outside this circle? Its vertex is outside this circle. This is angle NLP that subtends on chord NP and its vertex is located outside this circle. Actually, the size of this angle, NNP, is 39 degrees. This is less than 45 degrees. Actually, it is very easy to see that you can also try and check. You can draw any angle that is located outside this circle and subtend on chord NP. The size of the angle will be less than 45 degrees. You can check it by yourself. Likewise, all the angles that their vertices are located inside this circle and the subtend on chord NP will be greater than 45 degrees. Like this angle NOP, that its vertex is located inside this circle and the subtend on chord NP, the size of this angle NOP is 85 degrees. So in conclusion, you can say that all the angles that lie inside this circle and subtend on NP will be greater than 45 degrees, while all the angles that are located outside this circle and subtend on the same chord NP will be less than 45 degrees. The only angles that subtend on chord NP and are equal to 45 degrees in their sizes are located on the circle itself. Like those two angles, their vertices, they are located on the circle. Vertex Q is located on the circle and vertex M also located in this circle on the circle itself. Therefore, if we rotate angle NQP around this circle without changing its size, and chord NP will be the axis, we will not move the axis NP, we get infinite angles that each of them will be equal to 45 degrees in its size. Why? Because we did not change the size of the angle, we rotate only the vertex Q without changing the size of the angle. We create infinite angles that all of them will be equal to 45 degrees in their sizes, and they are all subtend on chord NP because chord NP is not moving. One of the angles will be angle PMN, that is equal to 45 degrees in its size because we will not change the size of the angle and it subtend on chord NP. In the next step, we will join points M and Q together by straight line. In this way, we created quadrilateral NMQP. This is exactly the same quadrilateral NMQP because we have angle PMN that is equal to 45 degrees in size and it subtend on chord NP. Here we have also angle M. We have angle MPN. We have angle PMN. This is equal to 45 degrees in size and is subtend on the same chord called PN. So we created quadrilateral MNQP. We join points M and Q together by straight line. In this way we created quadrilateral NMQP. Quadrilateral NMQP is definitely inscribed by this circle. It is blocked by this circle. Why? Because of the fact that all the four vertices N, M, Q, and P lie on the circle itself. Therefore, quadrilateral NMQP is inscribed by this circle. In conclusion, you can say that quadrilateral NMQP is a cyclic quadrilateral. So if we found out that quadrilateral MNQP is a cyclic quadrilateral, it means that you can block this quadrilateral NMQP by the red circle. Quadrilateral NMQP is blocked by this circle because of the fact that all the four vertices of quadrilateral NMQP lie on the red circle. This is point N, M, Q, and P. They all lie on the red circle, and therefore quadrilateral NMQP is inscribed by this red circle. We also have the rule that says that the sum of the opposite angles of a cyclic quadrilateral is equal to 180 degrees. So the sum of those two opposite angles, the cyclic quadrilateral NMQP, must be equal to 180 degrees. This is angle NPQ, that is right angle. This is angle NMQ, that is equal to 45 degrees plus x. And again, according to the rule that I mentioned, the sum of two opposite angles of a cyclic quadrilateral is equal to 180 degrees. So angle any quadrilateral NMQP, angle NPQ plus the opposite angle NMQ total must be equal to 180 degrees according to the rule that I presented to you. Angle NQP is a right angle and angle NMQ equals to 45 degrees plus x. So again, angle NQP is a right angle and angle NMQ equals to 45 degrees plus x. And in total, they must be equal to 180 degrees. 45 degrees plus 90 degrees is 135 degrees, so 135 degrees plus the missing angle x. In total, it must be equal to 180 degrees. Here we subtracted 125 degrees from this equation, and finally found out that the missing angle x equals to 180 degrees minus 135 degrees is 45 degrees. So the missing angle x, that is also defined as angle AMQ, is equal to 45 degrees on its side. Repeat again. Angle x, that is also defined as angle AMQ, equals to 45 degrees on its sides. So we finish with the first question. In the next step, I actually presented to the second question, and we solve the second question of this lecture. The second question, our task is to find out the area of this circle that is described by this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB. Therefore, quadrilateral ABCD is defined as a trapezoid because of the fact that it has one pair of parallel sides. If we know that the two parallel sides DC and AB are defined as the bases of trapezoid ABCD. So if we define the length of the base DC as A, and the length of the base AB is B, then the area of this trapezoid ABCD will be equal to A plus B. That is the sum of its two parallel bases times the height edge over 2. The height edge must create 90 degrees with its two parallel bases. So in conclusion, we can say that a trapezoid is a quadrilateral with one pair of parallel sides, and the area of one trapezoid equals to the sum of its two parallel bases. In this case, this is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So repeat again, in the drawing, we have a circle that is described by this trapezoid ABCD. In addition, we know that those two angles are both right angles. We also know that side AB of trapezoid ABCD equals to 3 units in its length, and the area of this trapezoid ABCD is equal to 3 square units in its size. Again, our task is to find out the area of this circle that is described by this trapezoid ABCD. We can say that also trapezoid ABCD blocks this circle. So in the first step, we define the relevant points to this question with letters. We define the center of this circle, this point is point O. Likewise, we define the point of tendency of tangent DC with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. We define the point of tendency of tangent AB with this circle, this point is point G. In addition, we define the radius of this circle as x. In the next step, we join points O and G together by a straight line. Point O is the center of the circle, point G is the point on the circle itself, therefore OG is the radius of the circle, this is equals to x according to our definition. The radius of OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, that is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. Likewise, we join points O and D together by straight line. OE is the radius of this circle, that is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2 free vertices. 1, 2 free vertices. The sum of free vertices 3 right angles is equal to 270 degrees. So 270 degrees plus the size of this fourth triangle in total must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth triangle must be equal to 90 degrees in its side. So inside quadrilateral EDF4 we have 4 right angles, and therefore can relate to quadrilateral EDF4 is a rectangle, although that it is a square. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle EDF4, side EO must be equal to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrilateral F4GA, we have 1, 2, 3 right angles, and therefore this fourth triangle must be equal to 90 degrees in its size, and therefore we can relate to quadrilateral F4GA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle F4GA, side OG must be equal to the opposite side FA. But GO is x, therefore the opposite side FA must be also equal to x units in its length. So in total, the length of side DA of trapezoid ABCD equals to x plus x, that is 2x. We define the length of side DC of trapezoid ABCD as A. We know that AB equals to 3 according to what is given in the question, and CB is the missing side, so leave it as it is. We have already proved in the previous lecture that DA plus CB equals to DC plus AB according to rule 1. And again, according to rule 2, of course. We already proved that in trapezoid ABCD, DA plus CB equals to DC plus AB. It is true actually for any trapezoid. Not necessarily to trapezoid ABCD, it is to any trapezoid. That is to say DA plus the opposite side CB equals to DC plus the opposite side AB, according to rule 2. DA equals to 2x plus CB is the missing side, so it is, and it is equals to DC. DC is A plus AB, that is 3. So total we found out that 2x plus CB equals to A plus 3. Here we subtracted 2x from this equation, and we found out that the missing side CB equals to A plus 3 minus 2x. This is the missing side CB, is equals to A plus 3 minus 2x units in its length. In the next step, we did a construction, that is to say from point C we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we can do quadrilateral DCMA. In quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth triangle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth triangle must be equal to 90 degrees in its size. So in quadrilateral DCMA, we have 4 right angles. Therefore, we can relate to quadrilateral DCMA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the ref of this missing line segment MB? MB equals to AB minus AM. Again, MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus AM in its length. In the next step, I copied the right triangle CMB in a new page and implemented the Pythagoras theorem in this right triangle CMB. According to the Pythagoras theorem in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CMB that I copied from the original drawing. According to the Pythagoras theorem in this right triangle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared, and it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. Plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So in total, we found out that A plus 3 minus 2x squared equals to 4x squared plus A plus 3 minus A squared. We open the brackets on both sides of this equation. According to the algebraic identity, that says that A plus B squared equals to A squared plus B squared minus 2 times A times B. According to the algebraic identity that I mentioned, A plus 3 minus 2x squared will be equal to A plus 3 squared plus 2x squared, that 2x squared is 4x squared, minus 2 times A plus 3 minus 2x. And it is equals to 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times a, that is minus 6a. Open the brackets of this expression and actually found out that a plus 3 squared equals to a squared plus 3 squared, that is 9, minus 2 plus 2 times a times 3, that is 6a. And we also have 4x squared minus 2 times 2x is minus 4x. So in total this expression equals to minus 4x times a plus 3, and that is equals to 4x squared plus 9 plus a squared plus a squared minus 6a. We have a squared on both sides of this equation, so a squared will cancel. We have 9 on both sides of this equation, so 9 also will cancel. And we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancel those two expressions, and this side of the equation we left only with 6a minus 4x times a plus 3, and on the other side of the equation we left only with minus 6a. So in total we should find out that 6a equals to minus 4x times a plus 3, and it is equals to minus 6a. Here we added 6a and also 4x plus a plus 3. We added 6a and also 4x times a plus 3 simultaneously to this equation. If I found out that 6a plus 6a is 12a, so 12a equals to 4x times a plus 3. Here we divided this equation by 2, and if I found out that 12a over 2 is 3a, 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divided this equation by a plus 3, and finally found out that x equals to 3a over a plus 3. The next step, we calculated the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. And the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB times the height CM over 2. Why CM is the height? Because it creates 90 degrees with the two parallel bases. Repeat again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say DC plus AB times the height CM over 2. The area of trapezoid ABCD equals to the sum of its two parallel bases, that is also DC plus AB times the height CM over 2. DC is A, plus AB is 3, and CM is 2x. Repeat again, DC is A, AB is 3, and CM is 2x divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have only a plus 3 times x. So in total we found out that the area of trapezoid ABCD equals to a plus 3 times x square units in its size. But it is given us the question that the area of this trapezoid ABCD equals to 3 square units in its size. Therefore we can substitute the area of trapezoid ABCD by 3 square units. So we substituted the area of trapezoid ABCD by 3 square units. So 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3. So we can substitute x in this equation by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. So in total we found out that 3 equals to 3 equals to a plus 3 times 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 gets cancelled, and we left only with 3 equals to 3a. And again, we found out that 3 equals to 3a. Here we divided this equation by 3, and found out that a equals to 1. A equals to 1, but we already found out that x equals to 3a over a plus 3, so we can substitute a in this equation by 1 because a equals to 1. We did it, and we found out that x equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total we found out that the radius of the circle is equal to 3/4 units in its length. Our test is to find out the area of this circle that is described by trapezoid ABCD. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. x is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total we should find out that the area that you are looking for in this question, that is the area of this circle, equals to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle was to 1.767 square units in its size. Okay, thank you very much.